In this talk, I'm going to describe a Fisher formalism for anisotropic gravitational-wave background searches with PTAs. This work was put out on the archive and has this phone number here, and it's work that I've done in collaboration with Yassine Ali Hamoud and Chiara Mingarelli. So let me first establish why it is interesting to look for anisotropies in the PTA gravitational wave background. We know that the gravitational wave background that we see from PTAs, if it's produced by supermassive black hole binaries, is going to have some level of Poisson fluctuation, since some of the sources that we'll see will be closer and brighter than others. So there are a few ways of making an estimate of how much this will contribute to an anisotropy, but those ways all give pretty much the same answer, which is about a 1% anisotropy. And one of the ways to see that is described in this Nature Astronomy paper by Chiara Mingarelli and others from 2017. Another reason that we expect some level of anisotropy in the PTA gravitational wave background is that supermassive black hole binaries are going to trace large-scale structure. And we know that large-scale structure itself is anisotropic at the level on these scales. So PTAs are probing the largest scales corresponding to the smallest multipoles, which might give us not even an estimate, but a suggestion of, again, 1% anisotropy coming from that source. And then there are other sources of gravitational wave backgrounds that may have their own anisotropies, such as cosmic strings and primordial black holes. So since we're going to be talking about anisotropies of the gravitational wave background, I want to first establish a notation that I'm going to use throughout the talk and is used in our paper. And that is, when we're thinking about some map on the sky, here I've written it as a function m of omega hat, we're going to think about that as a vector. So we're going to translate that into a vector m, shown by this bold symbol m here. And we can take dot products of maps, and we'll define our dot product this way. So if we have two maps, m and n, and we take their dot product, that's the same thing as taking the function that they describe on the sky and integrating their product over the entire sky and then dividing by 4 pi. So computing the average of that of the product of the two maps over the entire sky. This is going to allow us to translate our results into standard linear algebra and will give us some very useful ways of understanding the information content of pulsar timing arrays in terms of their ability to tell us something about anisotropies in the gravitational wave background. So using this notation, we can write the correlated timing residual between two pulsars given at locations p hat and q hat by this simple expression. So this quantity here is what we call the pairwise response function, or is also known as the overlap reduction function. And when we dot that with some gravitational wave background, which is a function of frequency and position on the sky, this gives us the correlated TOA response for that pair. And we can plot what this function looks like as a function of the separation between the pair of pulsars that we're looking at. So this just describes that as we increase the angular separation between those two pulsars. One quick aside, but actually is something important to consider, in this paper we derive a geometric expression for this pairwise response function. And this is a very useful form to write the response function in for many reasons, but one of them is that we can immediately see what happens if we have an anisotropic gravitational wave background and we consider autocorrelations between the TOAs of a single pulsar. When we do that, we can see that the autocorrelation of a single pulsar in the presence of an anisotropic gravitational wave background responds not only to the monopole, but also has a dipole and a quadrupole response. So this is important to keep in mind if searching for anisotropies in the gravitational wave background, And in that search, if you incorporate the autocorrelations, you need to account for how the autocorrelations respond to the anisotropies that you're searching for. So to set the stage for what we're doing in this paper, I want to discuss two different ways that have been presented in the literature to look for anisotropies in the gravitational wave background using pulsar timing arrays. The first involves looking at the Hellings and Downs curve. So here I'm showing the Hellings and Downs curve for an isotropic background. But for an anisotropic background, as discussed in this paper by Steve Taylor and Jonathan Gare, when you have anisotropies, you will find there is scatter within the correlation, angular correlation in the timing residuals of pairs of pulsars. So this may be one way you might search for anisotropies using a PTA. Another way that's appeared in the literature is to look for and constrain the power spectrum, or the spherical harmonic amplitudes that would describe anisotropies in the gravitational wave background. And this is what was done in this paper by Steve Taylor, Karen Mingarelli, and others in 2013, applied to the European pulsar timing array. So the work that I'm describing here allows us to understand the optimal way of searching for anisotropies in a gravitational wave background, and also helps to clarify some of the results, such as the one I show here, that have appeared in the literature. Applications of our ideas to a realistic pulsar timing array is described in the talk by Yassine Ali Hamoud, so I encourage you to watch that talk as well. But here we're going to consider something more abstract, or a toy model of what a PTA is. So the residual likelihood can be written in this way using our notation. So here is the correlated time of arrival between unique pairs of pulsars. So I here and J represent pairs of pulsars. And then this is the expected response given some gravitational wave background intensity map I. And here we're just assuming that these correlated TOAs between pairs of pulsars are Gaussian distributed. We can define dual response maps. So this asterisk here does not indicate complex conjugation, but it means that there are maps that are dual to the response maps, such that when we take their dot product, we get a Kronecker delta. That allows us to define gravitational wave background map estimators I hat, and then it's straightforward to take these quantities and rewrite this likelihood as a likelihood for I hat in this way. And so here in the middle, we have our inverse covariance matrix, also known as the Fisher matrix, that describes the information contained within this likelihood. So to make, oh, and I should say that in the map space, one aspect or one result of writing the inverse covariance matrix this way is we can immediately see that this matrix here, thought of as a matrix with vectors in map space, has n pair dimensions. This is a result that we show rigorously in our paper. So it automatically tells us that the maximum number of parameters that any gravitational wave background search can constrain is n pair, as long as we're not including other priors from other sources. So we have only n pair pieces of information we can extract. So to make further progress with our PTA Fisher, we need to have an expression for this inverse covariance here for the pairs I and J. And we use the weak signal limit to write that down. So we're working in band powers. So delta F is the width of any given band power that we're working in. And then we just have a simple expression here for the noise in each of the two pulsars P and Q within a given pair. So this is diagonal, and that's what simplifies our expression. Also in this paper, we work with a simplified noise model where we assume that each pulsar just has a white noise associated with it of 100 nanoseconds with a cadence of 20 measurements per year. And I want to point out, though, that these approximations in terms of how we're modeling the noise are not necessary. We can use Hassasiyah to produce more realistic noise curves for each pulsar, which is exactly what we've done in our follow-up paper that's described by Yassine Ali Hamoud. So one of the immediate results we get from this, this formalism is an understanding of what a PTA can see in the gravitational wave background and what it cannot see. So we can divide any given intensity map into two terms, where this I perpendicular is a map whose dot product with the pairwise response functions for every pair in the PTA is equal to 0. So this map is going to project out to 0 when we put it into our Fisher matrix, which means that it is invisible to this particular PTA. Something similar to this was discussed in this paper by Cornish and Van Hasteren, applied to continuous waves. Here we're looking at this property for a search for a gravitational wave background. And just to show you an example, if we take, quote, the 6 best ePTA pulsars, these are the 6 best pulsars when searching for continuous waves, we can produce a map that has a strong anisotropy, but this map, when projected onto a PTA consisting of these 6 pulsars, will have just a monopole. You will not see any anisotropy whatsoever. One other thing that we can do that is essential in understanding the information content of a PTA is to define what we call principal maps. These are just the unit eigenmaps of the Fisher matrix. So we can find these unit eigenmaps whose eigenvalue is 1 over the square of the noise of the amplitude of that map. And we've shown analytically that in the dense and isotropic limit, these principal maps are equal to the real spherical harmonics. And we can actually see that progression here. So if we imagine having a PTA that has 10 pulsars quasi-isotropically distributed on the sky, these are the first 5 principal maps. And the structure is not really recognizable, but these turn out to be the eigenmaps of the Fisher matrix for this PTA. If we zoom ahead and look at a PTA that has 90 pulsars that are isotropically distributed, these patterns look familiar. We have a monopole, we've got a dipole, and we have some pieces, I should say this, some pieces of higher order real spherical harmonics. And in fact, if we break this out in a slightly different way, we can compute the ratio of the noise in the monopole to the noise in any one of the principal maps as we increase the number of pulsars, and then we can derive what this ratio is in the case where we have an infinite number of pulsars. And in that case, you can actually see the monopole, the quadrupole, the dipole, and higher order multipoles appearing here. And as we decrease the number of pulsars in our PTA, we deviate from this idealized limit. And so this is giving us some sense, which I'll talk about in a few slides, that when applied to a realistic PTA, this dense isotropic limit represented by the black points here do not describe the information content in a realistic PTA. But sticking with our dense isotropic limit, we can demonstrate the power of this approach by noting that we can think about modeling different types of anisotropies and make statements about how sensitive a PTA is to those anisotropies. So if we expand our gravitational wave background in terms of the real spherical harmonics, our formalism allows us to say that for the dense isotropic PTA, the minimum dipole is approximately 28 over the SNR in the monopole. So we would need a fairly large signal-to-noise measurement of the monopole before we become sensitive to a dipole in that gravitational wave background. We can also consider what happens when we have a stochastic hotspot in a known location. I want to emphasize that this is just a toy model. This hotspot itself is stochastic, which is very unrealistic when thinking about the gravitational wave background measured by a PTA, but it's a useful toy to look at to think about the sensitivity of a PTA to anisotropies. And it turns out that the signal to noise in the monopole necessary to detect the presence of a hotspot is not very large. We don't need a very large SNR for the monopole before hotspot sensitivity becomes noticeable, becomes significant. So finally, I want to end by making a bridge between what I'm talking about here and what Yassine will be talking about in his talk on the follow-up paper that we are finishing right now. And that is what happens when we have a realistic pulsar timing array. So a realistic pulsar timing array is different from the dense isotropic limit in two important ways. One, there aren't as many pulsars that that are part of the PTA, and two, more importantly, the distribution of those pulsars is anisotropic. So we can see this is a location of the pulsars in the nanograv 11-year dataset, and we can compute using our Fisher matrix the pixel by pixel inverse covariance of the pixel by pixel Fisher matrix, and it looks something like this. I don't want you to take anything quantitative away from this, but qualitatively we can see the particular way in which the covariance behaves, or the inverse covariance behaves pixel by pixel for this PTA. And this is contrasted with what happens if we have a dense Fisher matrix, which is given by this pixel by pixel matrix here. So we can see by eye that the information content in an anisotropic realistic PTA is very different than one from a dense isotropic PTA. So let me summarize with the key points from my talk. The first, which might have gone by too quickly, but I want to emphasize here, what we've shown explicitly is that autocorrelations are sensitive to not only the monopole, but also the dipole and quadrupole of a gravitational wave background. We've presented a flexible and realistic Fisher matrix to describe PTA measurements. And from this Fisher matrix, we can show that PTAs are only sensitive to a finite number of gravitational wave background parameters, in particular n pair, so the number of pairs, of unique pairs of pulsars in the PTA. Everything that a PTA can see is described by the principal maps. So we can use that as a complete basis on the space of gravitational wave background maps that are observable by a given PTA. We have analytic results for a dense and isotropic PTA, which just gives us confidence that our numerical results are working out properly, but in no way is this limit related to anything realistic. And in order to see the application of our formalism to a realistic PTA, go watch Yassine Ali Hamoud's talk, and you'll see a lot of really interesting additional conclusions that we can reach when we apply this formalism to a realistic PTA.